You were taught that gravity is understood, that Einstein figured it out in 1915. Curved spacetime. Mass bends the fabric of the universe. Objects follow the curves. You have seen the rubber sheet analogy 100 times. A bowling ball on a trampoline. Marbles rolling toward the dip. It is clean. It is elegant. It is one of the most successful theories in the history of science. And it does not explain gravity, not even a little. What Einstein gave us is a description, an extraordinarily precise description. A description so accurate that it predicted gravitational waves a full century before we detected them. A description so reliable that your phone uses it right now to correct GPS signals that would drift by about 10 kilometers a day without relativistic adjustments. But a description is not an explanation. Einstein told us how gravity behaves. He told us what it does to the geometry of space and time. He never told us what it is. He never told us why mass bends space-time. He replaced the question, why do objects attract each other, with a question, why does mass curve the geometry of the universe? And then he never answered the new question. Nobody has. Not in the 110 years since he published the field equations. Not in the 350 years since Newton first wrote down the math. And here is the part that should genuinely disturb you. The people whose entire careers are built on answering this question are not converging on an answer. They are diverging. They are fracturing into camps that barely speak to each other. One group has spent 55 years developing a theory that has never produced a single testable prediction. Another group has built a mathematical framework so radical that time itself disappears from the equations. A physicist at University College London has placed a 5,000 to 1 bet against the majority position of his own field. One of the most prominent critics of theoretical physics left academia entirely in 2024 to become a YouTuber, and nobody organized the 2026 edition of the most important annual conference in string theory. Think about what that means. The flagship gathering of the largest research program in theoretical physics, and nobody stepped up to host it. You were told gravity was solved. It was never solved. It was described. And the difference between those two things is the deepest open wound in all of physics. Everything that follows from here pulls on a single thread. What is gravity? Not how does it behave? Not what are its effects? What is it? That question has been asked continuously for 3.5 centuries, and every answer ever given has turned out to be another description wearing the disguise of an explanation. Newton described it as a force. Einstein described it as geometry. Quantum theorists have tried to describe it as a particle. Thermodynamic theorists have tried to describe it as entropy. Every one of them reproduced the predictions. Every one of them pushed the mystery one layer deeper. And there is a pattern there that nobody in popular science communication wants to say out loud, because the pattern suggests something uncomfortable about the limits of physics itself. But before we get to that, we need to go back to the beginning, not to Einstein. Further back, to a 23-year-old man alone in a farmhouse during a plague, watching an apple fall from a tree and asking a question that would torment him for the rest of his life. The year is 1665. England is being gutted by the bubonic plague. Cambridge University has sent its students home indefinitely. Isaac Newton is 23 years old, and he has returned to his family's farm in Woolsthorpe, Lincolnshire. He is alone. He has almost no contact with other scholars. He has nothing but time and his own mind, which will turn out to be one of the most dangerous minds in the history of human civilization. The apple story is real, or close to real. The primary source is William Stukeley's memoir, based on a conversation with Newton on April 15, 1726, when Newton was 83 years old. After dinner, Stukeley recorded, "The weather was warm and they sat under apple trees in the garden. Newton told him that he was in just the same situation as when formerly the notion of gravitation came into his mind. He was sitting in a contemplative mood. An apple fell, and the question that entered his mind was not, why did it fall, but something far stranger. Why does the apple always fall perpendicularly to the ground? Why not sideways? Why not upward? What is it about the earth that commands the apple to move directly toward its center? The apple never hit him on the head. That embellishment was invented more than a century later, probably by Isaac Disraeli in the 1820s. The real story is more interesting because it reveals something about how Newton actually thought. He was not startled into a discovery by a bump on the skull. He was staring at something every human being in history had seen, a falling object, and asking why it falls in that particular direction. It is the kind of question that sounds trivial until you realize that nobody before him had ever framed it that way. And it is the kind of question that 360 years later still does not have an answer. Between 1665 and 1687, Newton built the mathematical framework that would define physics for over 2 centuries. The inverse square law, the law of universal gravitation. The idea that the same force pulling the apple downward was also holding the moon in orbit around the Earth and the Earth in orbit around the sun. It was a unification of breathtaking scope. Terrestrial and celestial mechanics, which had been considered completely separate domains since Aristotle, were revealed to be the same phenomenon. And the math worked. It worked so precisely that astronomers could predict eclipses, calculate orbits, and eventually navigate spacecraft to other planets using Newton's equations alone. But here is the thing Newton himself could never get past. His equations told you how to calculate the gravitational force between any two masses. They told you the force was proportional to the product of the masses and inversely proportional to the square of the distance between them. They told you everything you needed to predict what gravity would do, and they told you absolutely nothing about what gravity is or how it works. The equation says that two objects separated by empty space somehow pull on each other instantaneously, across any distance, with nothing between them mediating the interaction. Mass here affects mass there, right now, with no delay and no mechanism. Newton hated this. He did not merely dislike it as an aesthetic flaw, he found it intellectually repulsive. In his third letter to the theologian Richard Bentley, written in 1692, 5 years after the Principia was published, Newton wrote one of the most remarkable confessions in the history of science: that one body may act upon another at a distance through a vacuum without the mediation of anything else, by and through which their action and force may be conveyed from one another, is to me so great an absurdity that, I believe, no man who has in philosophic matters a competent faculty of thinking could ever fall into it. Read that again. The man who discovered universal gravitation is calling the core mechanism of his own theory a great absurdity. He is saying that any rational person should find action at a distance unbelievable. And he is saying this 5 years after publishing the theory, meaning he spent those 5 years trying to find a deeper mechanism and failing. His response to this failure became one of the most quoted phrases in scientific history. In the General Scholium appended to the second edition of the Principia, in 1713, Newton wrote in Latin, "Hypotheses non fingo."
I do not feign hypotheses.
I will not invent explanations for things I cannot deduce from the data. It sounds like intellectual discipline. It reads like a statement of scientific rigor. But in context, it is something much darker. It is a surrender. Newton is saying, I have built the most successful theory of nature ever created. It describes the behavior of every object in the universe, and I cannot tell you what it means. I cannot tell you why it works. I cannot tell you what gravity actually is. And I am done trying. He spent the remaining decades of his life not trying to answer that question, but trying to destroy anyone who threatened his ownership of the description. His war with Robert Hooke consumed years. Hooke had suggested the inverse square law in a 1679 letter and later claimed publicly that Newton had stolen the idea. Newton's revenge was meticulous and permanent. He rewrote sections of the Principia in dense geometric propositions, specifically so Hooke could not follow them. He told a colleague he wanted to avoid being baited by little smatterers in mathematics. After Hooke died in 1703, Newton became president of the Royal Society. During his tenure, the only known portrait of Robert Hooke vanished. Whether Newton ordered its destruction has never been proven, but no portrait of Hooke has ever been found. The calculus war with Gottfried Wilhelm Leibniz was worse. Newton developed his method of fluxions in 1664 through 1666, but did not publish. Leibniz independently published his version of calculus in 1684. The dispute over who deserved credit escalated into the ugliest intellectual feud of the century. In 1712, the Royal Society convened a committee to adjudicate. Newton was president of the Royal Society. He is widely believed to have written the committee's report himself. It found, predictably, in his favor. Leibniz died in 1716, isolated and embittered. His funeral was attended only by a former secretary. A contemporary noted that Leibniz was buried more like a robber than what he really was, an ornament of his country. And the ironic consequence of Newton's victory was that British mathematics clung to his inferior notation for over a century, while continental mathematicians using Leibniz's superior system raced ahead. Newton won the battle and crippled British science. But none of this personal wreckage changes the central fact. Newton's equations work. They work spectacularly, and they explain nothing about what gravity actually is. That question sat open, untouched, for over 200 years. In 1798, Henry Cavendish managed to measure the gravitational force between objects in a laboratory for the first time, using a torsion balance designed by the late Reverend John Mitchell. Two small lead spheres, each weighing about 1.61 pounds, were suspended on the ends of a 6-foot wooden rod hanging from a thin wire. Two massive lead spheres, 348 pounds each, were brought near them. The gravitational attraction between the spheres produced a force of approximately 1.74 times 10 to the negative 7 newtons. That is the weight of about 18 micrograms, roughly the weight of a single grain of pollen. The rod deflected by about 4 millimeters. Working in a sealed shed to prevent air currents and observing through telescopes mounted in the walls, Cavendish determined the density of the Earth at 5.448 times the density of water, within about 1% of the modern accepted value. The precision of this measurement was not surpassed for nearly a century. And here is a detail about the gravitational constant that should bother you far more than it does. G, the gravitational constant, is known today to about 5 significant digits. Its accepted value is 6.67430 times 10 to the negative 11 cubic meters per kilogram per second squared, with an uncertainty of plus or minus 31 in the last 2 digits. That gives it a relative uncertainty of about 47 parts per million. For comparison, the fine structure constant governing electromagnetism is known to about 12 significant digits. Planck's constant is known to 9. The speed of light is defined exactly. G is the worst measured fundamental constant in all of physics. Over 300 experiments across more than 2 centuries have tried to pin it down, and the spread between the highest and lowest modern measurements exceeds 500 parts per million. In 2018, researchers at China's Huazhong University of Science and Technology published what were then the most precise measurements ever made of G. They used 2 completely different methods. Both were exquisite feats of experimental physics, and the 2 results disagreed with each other. Think about that. Gravity is the first force human beings ever experienced. It is the force you are feeling right now. It governs the orbits of planets and the structure of the entire cosmos. And after 300 experiments over 2 centuries, we cannot even measure its strength accurately. There is something about gravity that resists being pinned down at the most basic level. And the fact that this is not front-page news, that you have almost certainly never heard about the G measurement problem, tells you something about how physics communicates with the public. The embarrassments get buried. The clean stories get told. Newton described gravity. Cavendish measured it. But after 200 years, the question Newton refused to answer remained completely open. What is gravity? Why do masses attract? What is the mechanism? And in 1907, a 28-year-old patent clerk in Bern, Switzerland, had what he later called the happiest thought of his life. A thought that would, over the next 8 years, lead him to the most beautiful and most misleading theory in the history of physics. Albert Einstein was not thinking about gravity when gravity found him. He was sitting in a chair at the Swiss Patent Office in Bern in 1907, reviewing patent applications, when a thought struck him that he later described as der glücklichste Gedanke meines Lebens, the happiest thought of my life. The thought was this: if a person falls freely, they will not feel their own weight. It sounds simple, almost obvious, but Einstein recognized something in that statement that nobody before him had grasped. If you are in free fall, there is no experiment you can perform inside your falling elevator that will tell you whether you are falling in a gravitational field or floating in empty space far from any mass. Gravity and acceleration are locally identical. This is the equivalence principle, and it became the foundation on which Einstein rebuilt our entire understanding of gravity. But the equivalence principle is also, if you think about it carefully, deeply strange. It says that gravity is not like other forces. Electromagnetism acts differently on different charges. The strong force acts differently on different quarks. But gravity acts on everything identically, regardless of mass, composition, or internal structure. A feather and a hammer fall at the same rate in a vacuum. This has been confirmed to extraordinary precision. In 2202, the microscope satellite measured the equivalence principle to an accuracy of 2.7 times 10 to the negative 15. That means for every quadrillion units of gravitational and inertial mass, they agree to within about 3 units. No other principle in physics has been tested to this precision. And that universality is what led Einstein to his radical reinterpretation. If gravity affects everything identically, perhaps gravity is not a force acting on objects at all. Perhaps it is a property of the space and time through which objects move. Perhaps what we call gravity is just the natural geometry of the universe, and objects in gravitational fields are simply following the straightest possible paths through curved space-time. This was the seed. Growing it into a full theory nearly destroyed him. The mathematics Einstein needed did not exist in his toolbox. He was a physicist with strong intuition, but by his own admission, limited mathematical training compared to what the problem required. In 1912, he turned to his old classmate Marcel Grossmann at the Swiss Federal Polytechnic in Zurich. Grossmann had been the meticulous student who took careful notes in the lectures Einstein skipped. Grossmann's father had written a letter of recommendation that helped Einstein get the patent office job when no university would hire him. Now Grossmann would save Einstein's intellectual life a second time. Grossmann introduced Einstein to the work of Bernhard Riemann, Gregorio Ricci-Curbastro, and Tullio Levi-Civita, Riemannian geometry, tensor calculus, the mathematical language needed to describe curved spaces of any dimension. Einstein later wrote, "Grossmann introduced me to the work of Riemann, Ricci, and Levi-Civita. Without him, I would not have found my way." In 1913, they co-published what is now called the Entwurf paper, an early version of the field equations that was not yet fully correct. The equations were not generally covariant, meaning they did not hold the same form in all coordinate systems. And Einstein knew this was a problem, but could not yet fix it. 3 more years of struggle followed. Einstein described this period as the most intense intellectual effort of his life. He made errors, he published incorrect versions, he went down blind alleys that cost months. And then, in November 1915, the crisis came to a head. Einstein delivered 4 lectures to the Prussian Academy of Sciences in Berlin on 4 consecutive Thursdays, November 4th, 11th, 18th, and 25th. Each lecture presented a more refined version of his gravitational field equations. Between the 3rd and 4th lectures, he received a letter from the mathematician David Hilbert in Göttingen, revealing that Hilbert was working on the same problem and had arrived at very similar equations. On November 20th, Hilbert presented his own version to the Göttingen Academy, 5 days before Einstein's final lecture. Einstein was shaken. He complained in letters that Hilbert was trying to nostrify his theory, a term meaning to claim a foreign discovery as one's own. The priority question lingered for decades, but page proofs of Hilbert's original paper, discovered in the late 1990s, showed that his initial version was not fully generally covariant. The final published version, which matched Einstein's equations, was revised after Einstein's November 25th lecture. Hilbert himself eventually conceded graciously. Einstein did the work, he said, and not the mathematicians. On November 25, 1915, Einstein presented the final correct form of his field equations. They are, in the compact notation physicists use, g mu nu plus lambda g mu nu equals kappa t mu nu. The left side describes the curvature of space-time, the right side describes the distribution of mass and energy. The equation links them. Mass and energy tell space-time how to curve. Space-time tells mass and energy how to move. John Archibald Wheeler would later distill this into his famous one-liner. Space-time tells matter how to move. Matter tells space-time how to curve. And it works. It works stunningly. In 1919, Arthur Eddington led 2 expeditions to observe a total solar eclipse, one to Sobral in Brazil and one to the island of Principe off the west coast of Africa. They measured the deflection of starlight passing near the sun. Newton's theory predicted a deflection of about 0.87 arcseconds. Einstein's predicted 1.75 arcseconds, exactly double. Eddington's results matched Einstein. The Times of London declared, "Revolution in science, new theory of the universe, Newton's ideas overthrown." Einstein became the most famous scientist in the world overnight. And now here is the turn you were never told about. General relativity is the most precisely confirmed theory in the history of physics. It has passed every experimental test thrown at it for over a century. Gravitational lensing, gravitational redshift, the precession of Mercury's orbit, frame dragging, gravitational time dilation, gravitational waves. The predictions match the observations to extraordinary precision. In 2015, LIGO detected gravitational waves from merging black holes, and the waveform matched general relativity's prediction so closely that the residual, after subtracting the theoretical template, was pure noise. The theory is, for all practical purposes, perfect. But it does not explain gravity. It describes gravity in a different language than Newton used. Newton said gravity is a force that acts instantaneously at a distance. Einstein said gravity is the curvature of space-time caused by the presence of mass and energy. Einstein's description is better. It is more accurate. It accounts for things Newton's cannot. But it is still a description. Ask Einstein why mass curves space-time, and you get silence. The field equations tell you how much curvature a given distribution of mass produces. They do not tell you why mass has this property. They do not tell you what mechanism connects the presence of matter to the bending of the geometry around it. They take it as a given, an axiom, a starting point. This is the thing popular science never tells you. Wheeler's famous line, "Space-time tells matter how to move, matter tells space-time how to curve," is not an explanation. It is a slogan, a beautifully compact restatement of what the equations do. But it answers how and completely dodges why. Why does matter tell space-time how to curve? What is the mechanism? What mediates this interaction? Wheeler's slogan treats these questions as if they do not exist. And the rubber sheet analogy, the one you have seen in every popular science video and textbook since the 1960s, is worse than unhelpful. It is actively misleading. Picture the bowling ball on a rubber sheet with a marble rolling toward the depression. What causes the marble to roll toward the bowling ball? Gravity. The downward pull of the earth on the marble causes it to follow the curve in the sheet. The analogy uses gravity to explain gravity. It is perfectly circular. It explains nothing. It gives you a visual metaphor that feels like understanding while delivering none. And the fact that this is the primary tool used to teach general relativity to the public tells you something about how comfortable the physics establishment is with the appearance of explanation over the substance of it. So where does this leave us? Newton described gravity as a force and admitted the description was absurd. Einstein described gravity as geometry and never explained why the geometry responds to mass. Between them, they covered 228 years of the greatest physics ever done, and neither of them answered the question, what is gravity? The obvious next step, the step that worked brilliantly for every other force in nature, was to build a quantum theory. By the mid-20th century, quantum electrodynamics had been developed to describe the electromagnetic force with a precision of 11 decimal places. The strong nuclear force had been captured by quantum chromodynamics. The weak nuclear force had been unified with electromagnetism in the electroweak theory. 3 of the 4 fundamental forces had been successfully quantized, their behaviors explained by the exchange of particles: photons for electromagnetism, gluons for the strong force, W and Z bosons for the weak force. The pattern was clear. Forces are mediated by particles. Find the particle, build the quantum theory, and you have your explanation. For gravity, the hypothetical particle is the graviton. It would be massless because gravity has infinite range. It would be spin too because the source of gravity is the stress energy tensor, a second-rank tensor, unlike electromagnetism's spin 1 photon, whose source is the 4 current. The graviton is mathematically well motivated. It is theoretically elegant. And when physicists tried to build a quantum field theory around it, something happened that had never happened before with any other force. The math did not just produce wrong answers, it produced infinities that could not be removed. In quantum field theory, calculations routinely generate infinities. This is expected. The standard technique for handling them is called renormalization, a procedure that absorbs the infinities into a finite number of measurable parameters, the mass and charge of the particles involved. For quantum electrodynamics, this works. You get 2 parameters, the electron mass and the fine structure constant, and after absorbing the infinities into those parameters, every remaining prediction is finite and spectacularly accurate. For gravity, renormalization fails. Mark Goroff and Augusto Sagnotti proved in 1986 that at 2 loops in the perturbative expansion, gravity produces infinities that require entirely new counterterms to cancel. Each new order of calculation introduces more infinities requiring more counterterms, each with its own undetermined parameter. The theory does not converge. It does not stabilize, it spirals into infinite undetermined constants and loses all predictive power. Gravity is non-renormalizable. And the problem goes deeper than a technical failure with infinities. Much deeper. In ordinary quantum theory, particles move through space and time. Space and time are the stage. The particles are the actors. The stage is fixed. It does not participate in the physics, except as a background. But gravity, as Einstein showed, is not a force acting on a stage. Gravity is the stage. Space-time is not a fixed background on which gravitational interactions happen. Space-time is the thing that is gravitating. So when you try to quantize gravity, you are not quantizing a force on a fixed stage. You are trying to quantize the stage itself. You are trying to apply the rules of quantum mechanics to the very arena in which quantum mechanics is defined. The framework is trying to eat itself, and this is not a problem anyone knows how to solve. The scale at which quantum gravity effects become important is the Planck scale. The Planck length is 1.616 times 10 to the negative 35 meters. The Planck time is 5.39 times 10 to the negative 44 seconds. To put the Planck length in perspective, here is a comparison that the physicist Catherine Zurich of Caltech offered. If you enlarged a Planck length to the size of a grain of sand, then atoms would be the size of galaxies. The Planck scale is as far below an atom as an atom is below a galaxy. To probe it directly with a particle accelerator, you would need a collider the size of the Milky Way. The energy required, the Planck energy, is about 10 to the 19th gigaelectronvolts. The Large Hadron Collider at CERN reaches about 13,000 gigaelectronvolts. The gap between what we can reach and what we need to reach is a factor of roughly 10 to the 15th, a quadrillion, and there is no technology on any drawing board, no proposal in any grant application, no idea in any theorist's notebook that comes anywhere close to bridging it. So the most fundamental force in the universe resists quantization at the level of mathematics, resists probing at the level of experiment, and sits behind a wall of energy and distance that may be permanently beyond our reach. That is not a temporary problem waiting for a clever solution. That is a structural feature of reality. And the people who understand this best, who have spent decades running into these walls, have responded not with a unified push toward a solution, but with a fragmentation that tells its own story. The first response, and the one that consumed the most talent and funding, was string theory. The idea is elegant in its premise. Replace point particles with one-dimensional vibrating strings. Different vibrational modes produce different particles, and crucially, one mode of a closed string is a massless spin, two excitation, a graviton. Gravity emerges naturally from the theory without being put in by hand. When string theory was first developed in the late 1960s and early 1970s, this was electrifying. It seemed like the theory was telling physicists something deep about the structure of reality. Gravity was not just compatible with quantum mechanics and string theory. It was required by it. But string theory requires extra dimensions. Depending on the version, 6 or 7 additional spatial dimensions beyond the 3 we observe, for a total of 10 or 11. These extra dimensions are assumed to be compactified, curled up so small we cannot detect them. And the way these dimensions are compactified determines the physics that emerges in the 4 large dimensions we inhabit: the masses of particles, the strengths of forces, the value of the cosmological constant. Everything. The problem is that there is no unique way to compactify the extra dimensions. The number of possible configurations, known as the string theory landscape, was estimated by Raphael Bousseau and Joseph Polchinski in 2000 to be at least 10 to the 500th power. That number was later revised upward. Some estimates now place it at 10 to the 272,000th power. To give you a sense of what 10 to the 500th means, the number of atoms in the observable universe is approximately 10 to the 80. 10 to the 500th is not a large number. It is a number so large that the concept of largeness has ceased to apply. Each configuration gives you a different universe with different physical laws. String theory does not predict which one we live in. It is compatible with essentially any set of physical laws, which means, in the language of the philosopher Karl Popper, it is compatible with no observations. It cannot be falsified, it cannot be tested, it cannot be wrong is not, in any meaningful sense, a theory. Peter Woit, a mathematician at Columbia University, published Not Even Wrong in 2006. The title is borrowed from a phrase attributed to Wolfgang Pauli, who used it to describe ideas so vague they do not rise to the level of being incorrect. White argued that string theory is not a theory at all. It makes no predictions, even wrong ones, and this very lack of falsifiability is what has allowed the subject to survive and flourish. Lee Smolin, a physicist at the Perimeter Institute in Ontario, published The Trouble with Physics the same year. He wrote that the scenario of many unobserved universes plays the same logical role as the scenario of an intelligent designer. Each provides an untestable hypothesis that, if true, makes something improbable seem quite probable. These were not fringe critics lobbing grenades from outside. Woit is a respected mathematician at an Ivy League university. Smolin is a founding faculty member at one of the world's premier theoretical physics institutes, and their critiques, published simultaneously in 2006, were not refuted by the string theory community. They were deflected. The response was not, "Here is our prediction," And here is the experiment that will test it. The response was, the theory is too beautiful to be wrong, and we just need more time. That was 19 years ago. The predictions still have not come. The Large Hadron Collider, which began operations in 2008 at a cost of roughly $10 billion, was string theory's best hope for indirect evidence. Supersymmetric particles, which most versions of string theory require, were expected to appear at LHC energies. They did not appear. Not at 7 tera electron volts. Not at 13. Not at 14. The LHC found the Higgs boson in 2012, and then, for string theory, silence. 55 years, thousands of careers, billions in funding. No testable prediction, no experimental confirmation, no falsifiable claim. And at the Strings 2024 conference, Peter White reported that the mood was grim and that as of his writing, nobody had stepped up to organize Strings 2026, the most important annual gathering of the dominant research program in fundamental theoretical physics, and it could not find a host. That is not a theory going through a difficult period. That is a research program in a state of quiet institutional collapse. And the fact that string theory continues to be presented to the public as our best candidate for a theory of everything is not science communication, it is reputation management. But string theory's failure does not mean the problem has gone away. It means the problem is worse than anyone thought. Because the other approaches have not fared much better. In the 1960s, while most of theoretical physics was turning its attention to particle physics and the quantum field theories that would eventually produce the Standard Model, a handful of researchers were trying something far more audacious. They were trying to quantize gravity directly, not by embedding it in a larger framework like string theory, not by adding extra dimensions or new particles, just gravity, as Einstein described it, subjected to the rules of quantum mechanics. The most dramatic attempt was born in an airport. John Archibald Wheeler, the charismatic physicist who would later coin the term black hole, called Bryce DeWitt and proposed they meet during a layover. DeWitt arrived with the Hamilton-Jacobi equation of general relativity written out. His proposal was direct. Erwin Schrödinger had taken the Hamilton-Jacobi equation of classical mechanics, replaced the classical variables with quantum operators, and obtained the Schrödinger equation, the foundation of quantum mechanics. Why not do the same thing for gravity? Take the Hamilton-Jacobi equation of general relativity, promote it to a quantum equation, and see what comes out. What came out was the Wheeler-DeWitt equation, and what the Wheeler-DeWitt equation says about reality is one of the most disturbing results in the history of theoretical physics. The equation looks deceptively simple in its abstract form. H hat psi equals 0. The Hamiltonian operator acting on the wave function of the universe equals 0. But notice what is missing. In the Schrödinger equation, there is a time derivative on the left side. The wave function evolves in time. It changes. Things happen. In the Wheeler-DeWitt equation, there is no time derivative. None. The wave function does not evolve. It does not change. According to the most straightforward reading of this equation, the quantum state of the universe is static, frozen. This is called the frozen formalism problem, and it is not a minor technical issue. It strikes at the most basic feature of experienced reality. You are reading this, which means time is passing for you. Events are unfolding. Things are changing. But the fundamental equation of quantum gravity says the universe does not change. Time as a fundamental quantity is absent. It does not appear. It is not hiding somewhere in the mathematics waiting to be recovered through a clever calculation. It is simply not there. Either the equation is wrong, or our experience of time is an approximation of something deeper in which time does not exist. Neither option is comfortable. DeWitt's own life carried a weight of injustice that mirrors the difficulty of his work. He was born Carl Bryce Seligman. He changed his name after experiencing anti-Semitism as a young physicist working in Europe. Years later, the Nobel laureate Felix Bloch was so disturbed by the name change that he blocked DeWitt's appointment to Stanford University. DeWitt and his wife Cecile DeWitt Moret, also a distinguished physicist, built their careers instead at the University of Texas at Austin. His 1965 paper on the equation was delayed until 1967. The reason was absurd and revealing. His Air Force research grant had been terminated, and the Physical Review at the time refused to publish papers whose authors could not pay the page charges. The equation that describes the quantum state of the entire universe was held up by a billing dispute. The Wheeler-DeWitt equation remains unsolved in any physically meaningful sense. It was published in 1967. As of today, nearly 60 years later, nobody has extracted from it a prediction that can be tested against experiment. Nobody has convincingly shown how to recover the time-dependent universe we observe from its timeless framework. It sits in the literature like a locked door that everyone agrees is important and nobody can open. But at least the Wheeler-DeWitt approach tried to confront gravity head-on. There is another camp that decided the problem requires building gravity from the ground up, literally from the fabric of space itself. Loop quantum gravity, developed primarily by Abhay Ashtekar at Penn State, Carlo Rovelli at Aix-Marseille University, and Lee Smolin at the Perimeter Institute, begins with a radical premise. Space is not continuous. It is not the smooth, infinitely divisible fabric that Newton and Einstein assumed. It is made of discrete chunks, quanta of geometry. The smallest possible area is not zero. It is on the order of the Planck area, roughly 10 to the negative 70 square meters. The smallest possible volume is not zero either. Space is granular at the deepest level, like matter turned out to be granular when we discovered atoms. In loop quantum gravity, space is described by mathematical structures called spin networks, graphs whose edges carry quantum numbers representing discrete units of area and volume. When these spin networks evolve, they form spin foams, four-dimensional structures that represent the quantum evolution of geometry. Rovelli has said, "We have calculated Newton's law starting from a world with no space and no time. That is not hyperbole. In certain limits, Newton's familiar inverse square law drops out of the calculations, emerging from a fundamentally discrete, non-spatio-temporal foundation. The results are real. Loop quantum gravity has produced discrete spectra for area and volume operators, meaning geometry is quantized with specific allowed values, like electron energy levels in an atom. It has produced black hole entropy calculations that match the Bekenstein-Hawking formula connecting the microscopic quantum states to the macroscopic thermodynamic properties of black holes. And in a subfield called loop quantum cosmology, it has replaced the Big Bang singularity, the point where general relativity predicts infinite density and breaks down, with a big bounce, a previous contracting universe that bounced through a minimum volume instead of collapsing to a point. But loop quantum gravity has its own deep problems, recovering the smooth classical space-time of general relativity from the underlying discrete structure, showing that the quantum description reduces to Einstein's equations in the appropriate limit, has proven extraordinarily difficult and is not yet convincingly achieved. The theory does not include matter in a natural way. Adding particles to the framework is awkward and incomplete. And unlike string theory, which at least attempts to unify all four forces, loop quantum gravity is only a theory of gravity. It says nothing about electromagnetism, the strong force, or the weak force. It is a quantum theory of space-time that leaves everything else untouched. So string theory unifies everything but cannot make predictions. Loop quantum gravity makes predictions about geometry but cannot incorporate matter. These are the two largest research programs in quantum gravity. Between them, they employ the majority of the theorists working on the problem. And between them, after a combined total of roughly a century of work, neither has produced a testable prediction that has been confirmed by experiment. Then came the most radical proposal of all. In January 2010, Erik Verlinde, a respected string theorist at the University of Amsterdam, posted a paper called on the origin of gravity and the laws of Newton. His claim was audacious. Gravity is not a fundamental force at all. It is an entropic force, an emergent phenomenon arising from the statistical tendency of systems to move towards states of higher entropy. Just as the pressure of a gas is not a fundamental force, but an emergent property of trillions of molecules bouncing around, gravity is an emergent property of the underlying quantum information structure of the universe. Using the holographic principle, the Unruh temperature, and the equipartition theorem, Verlinde derived Newton's law of gravitation from first principles. The derivation is clean and startling. You start with information on a holographic screen, apply thermodynamic reasoning, and Newton's inverse square law appears. Verlinde then extended the argument to derive Einstein's field equations as well. Media coverage compared him to Einstein. The paper generated enormous excitement, but the excitement curdled quickly. In 2011, Kobakidze argued that experiments with ultra-cold neutrons were incompatible with the level of decoherence Verlinde's framework predicted. In 2017, Chris Pardo at Princeton found that the theory could not reproduce observed dwarf galaxy rotation curves. In 2018, Wang and Braunstein showed that the holographic screens central to the argument generally do not obey the first law of thermodynamics. A study of over 33,000 galaxies from Leiden Observatory found results consistent with Verlinde's predictions for small galaxies, but wildly inconsistent for large ones. Verlinde has not published a major paper on entropic gravity since 2016. In a 2021 interview, he said he was seriously considering rewriting my story from 2009, but now formulated much more precisely. That was 4 years ago. The rewrite has not appeared. The man who proposed the most radical reimagining of gravity in a century has gone quiet, and his silence is its own kind of data. And this brings us to a story that sits at the heart of this entire history, one that reveals what happens when the physics establishment encounters an idea it is not ready for. Not an idea about quantum gravity, but about gravity in its most extreme form. The idea that stars can collapse into objects so dense that nothing, not even light, can escape. In 1930, a 19-year-old Indian physics student named Subramanian Chandrasekhar boarded a ship from Bombay to Southampton. He had won a Government of India scholarship to study at Cambridge under the great astrophysicist Ralph Fowler. On the voyage, with nothing but time and his own intellect, Chandrasekhar worked out a calculation that would change the course of physics. He combined Einstein's special relativity with the quantum mechanics of electron degeneracy pressure and showed that there was an upper mass limit for white dwarf stars. Above roughly 1.44 solar masses, electron degeneracy pressure cannot support the star against gravitational collapse. The star must continue collapsing into something unknown, something with densities far beyond anything physics had contemplated. Chandrasekhar spent the next 4 years at Cambridge refining this result, which would become known as the Chandrasekhar limit. During that time, the most famous astrophysicist in Britain, Sir Arthur Eddington, the same man who had confirmed Einstein's general relativity during the 1919 eclipse expedition, regularly visited Chandrasekhar to check on his progress. Eddington appeared supportive, encouraging even. He showed genuine interest in the mathematics. On the evening of January 10, 1935, Eddington and Chandrasekhar dined together at Trinity College, Cambridge. During dinner, Eddington told the young Indian physicist, "I have asked the secretary of the society to give you extra time to speak." Chandrasekhar was grateful. The next day, at a meeting of the Royal Astronomical Society, Chandrasekhar presented his results, and then Eddington rose and publicly destroyed them. He declared that the combination of relativity and quantum mechanics was not born in lawful wedlock. He insisted there should be a law of nature to prevent a star from behaving in this absurd way. He used his authority, the authority of the man who had made Einstein famous, to dismiss the work of a 24-year-old who had nowhere near the institutional power to fight back. And Eddington never told Chandrasekhar in advance that he was going to attack. The dinner the night before, the extra speaking time, all of it now looked like a setup. Whether Eddington intended cruelty or simply assumed his authority was correction enough, the effect was devastating. Here is what makes this story relevant to the gravity question, and not just a historical footnote about scientific politics. The physicists who understood the math, people like Niels Bohr, Wolfgang Pauli, and Ralph Fowler, privately agreed that Chandrasekhar was right, and Eddington was wrong. Eddington's authority was simply too great. The man who confirmed general relativity had spoken, and a 24-year-old from India did not have the standing to override him. The consequence was decades of delayed progress. The concept that would eventually become the black hole, the most extreme expression of gravity in the known universe, was effectively suppressed for a generation. As the historian Arthur I. Miller wrote, Chandra's discovery might well have transformed and accelerated developments in both physics and astrophysics in the 1930s. It did not, because one man's authority mattered more than the mathematics. Chandrasekhar left Cambridge in 1937, never fully forgiving the institution. He went to the University of Chicago, where he spent a long and distinguished career. He won the Nobel Prize in Physics in 1983, nearly 50 years after Eddington's attack. But the damage to the field was already done. Our understanding of stellar collapse, neutron stars, and black holes was set back by decades because the most respected astronomer in the world preferred his intuition to a young man's calculations. And this pattern, authority suppressing uncomfortable implications about gravity, is not ancient history. It is playing out right now in real time across the entire field of quantum gravity. Consider what has happened in the last decade. In 2023, Jonathan Oppenheim at University College London published a paper in Physical Review X, proposing that spacetime might be fundamentally classical, not quantum. Not effectively classical or approximately classical, but fundamentally irreducibly classical, with stochastic fluctuations mediating the coupling between classical gravity and quantum matter. This is heresy. The default assumption of nearly every theoretical physicist alive is that gravity must be quantum at the Planck scale. Oppenheim is saying that assumption might be wrong. He placed a 5,000-to-1 bet with Carlo Rovelli and Jeff Pennington that spacetime is not quantized. 5,000-to-1. Those are not the odds of a crank, those are the odds of someone who has done the math and arrived at a conclusion that contradicts the majority of his colleagues, and who is willing to put his money and his reputation behind it. Oppenheim told a reporter, "When we started, maybe 99% of our colleagues thought we were crackpots, and that is now down to maybe 70%. A 24 paper by Grudke and colleagues showed that pure classical gravity in Oppenheim's framework is formally renormalizable, something quantum gravity famously is not. The theory is gaining traction precisely because the alternatives have stalled." Sabine Hossenfelder published Lost in Math in 2018, arguing that theoretical physics had been led astray by aesthetic criteria, beauty, naturalness, elegance, rather than empirical evidence. Her assessment of the field was blistering. Theoretical physicists used to explain what was observed. Now they try to explain why they cannot explain what was not observed. And they are not even good at that. By April 2024, she left full-time academic employment to become a YouTube creator. Her channel has over 1.7 million subscribers and nearly 300 million views. LMU Munich ended its affiliation with her in 2025. As of late 2025, her archive papers list her as looking for a new affiliation. The most prominent public critic of theoretical physics in the world was effectively pushed out of the institution. Whether that was the cause or the effect of her YouTube career is debatable. What is not debatable is what it signals about the state of the field. When the people who understand the problem best are leaving academia, placing bets against each other, going silent, and failing to organize their own conferences, you are not looking at a research program going through a rough patch. You are looking at a field in crisis. And the crisis is not about any one approach failing. String theory, loop quantum gravity, entropic gravity, the Wheeler-DeWitt equation, they have each contributed genuine insights. The crisis is about the pattern. Every approach that reproduces gravity's behavior, that correctly predicts the things we can measure, fails to explain what gravity actually is. Every approach that tries to go deeper than description ends up replacing one mystery with another. Newton replaced "Why do objects fall?" with "Why do masses attract at a distance?" Einstein replaced that with "Why does mass curve space-time?" String theory replaces that with "Why do strings exist and why do they vibrate?" Loop quantum gravity replaces it with "Why does space have a discrete quantum structure?" Entropic gravity replaces it "Why does information on a holographic boundary produce gravitational effects?" Each step reproduces the predictions. Each step pushes the why one level deeper, and none of them, not one, has ever hit bottom. That pattern is the thing nobody wants to talk about, because if it is not a series of failures waiting for an eventual success, if it is instead the structure of the problem itself, then it means something deeply uncomfortable about what physics can and cannot do. But before we confront that possibility head-on, there is one more layer to descend through, because the question is not just whether we can explain what gravity is. The question is whether gravity is even a thing in the first place, whether the force that holds you to the ground, that holds the Earth in orbit, that holds galaxies together, is a force at all, or whether it is something else entirely, something that, if the most radical interpretation of the evidence is correct, might not exist in any fundamental sense. Remember the equivalence principle, the thought that Einstein called the happiest of his life. If a person falls freely, they will not feel their own weight. The microscope satellite confirmed this in 2002 with a precision of 2.7 times 10 to the negative 15. Gravitational mass and inertial mass are identical to within a few parts per quadrillion. Now think about what that actually means. If you are in a windowless elevator in free fall towards the Earth, there is no experiment you can perform, no instrument you can build, no measurement you can take that will tell you whether you are falling in a gravitational field or floating in deep space, far from any mass. The two situations are physically indistinguishable. Inside the elevator, gravity has vanished. Not weakened, not partially cancelled, vanished. There is no local measurement that can detect it. In general relativity, this is not a curiosity or a useful approximation. It is the foundation. Objects in freefall are not being pulled by a force. They are following geodesics, the straightest possible paths through curved space-time. A planet orbiting a star is not being held in its orbit by a pull. It is traveling in a straight line through a geometry that happens to curve back on itself. There is no force acting on it. The apparent acceleration of the planet is entirely due to the curvature of the geometry. In this picture, gravity is not a force. It is a property of the stage. And when you remove the stage from the discussion, when you look at the experience of a freely falling object from the inside, gravity is simply absent. So is gravity a force? In Newton's framework, absolutely. It is a force, clearly defined, with a direction and a magnitude. In Einstein's framework, not really. It is geometry. But in quantum field theory, forces are mediated by particle exchange, photons for electromagnetism, gluons for the strong force. If gravity is geometry, what does it even mean to look for a graviton? Are we quantizing a force, a property of space-time, or the arena itself? In 1995, Ted Jacobson at the University of Maryland published a paper that to this day has not been fully absorbed by the physics community. It was titled Thermodynamics of Space-Time, the Einstein Equation of State. What Jacobson showed is that Einstein's field equations, the foundation of general relativity, can be derived from thermodynamics, specifically from the Clausius relation delta Q equals T delta S, applied to local causal horizons. Heat flow across a horizon equals the temperature times the change in entropy. Starting from this thermodynamic relation and the equivalence principle, Jacobson derived the Einstein field equations. The implication is staggering. If Einstein's equations are derivable from thermodynamics, then they are not fundamental laws. They are an equation of state. Like the ideal gas law, PV equals nRT, which describes the macroscopic behavior of a gas without telling you anything about the individual molecules, the gas law is real, it works. You can engineer with it, but it is not fundamental physics. It is statistics. Jacobson's result suggests that general relativity might occupy the same status. Not a fundamental law of nature, but a macroscopic statistical description of something deeper, something involving microscopic degrees of freedom that we have not yet identified. And this is where the holographic principle enters and where the conceptual ground beneath your feet drops away entirely. In 1993, the Dutch physicist Gerard Hooft and in 1995, Leonard Susskind elaborated that the maximum amount of information that can be stored in a region of space is proportional not to the volume of the region, but to the area of its boundary. This is the holographic principle. It says, in effect, that everything happening inside a volume of space can be completely described by data encoded on the surface surrounding it. The three-dimensional interior is redundant. The boundary contains everything. If that sounds like a mathematical curiosity with no physical consequences, Juan Maldacena proved otherwise in 1997. His ADS/CFT correspondence, which has accumulated over 10,000 citations and is one of the most cited papers in the history of theoretical physics, demonstrated something extraordinary. A gravitational theory in a five-dimensional space-time with a negative cosmological constant is exactly, precisely, completely equivalent to a quantum field theory on its four-dimensional boundary. And the boundary theory contains no gravity. None. Gravity in the interior, the bulk, is a consequence of quantum entanglement on the boundary. It is not a separate force. It is not a fundamental ingredient. It emerges from quantum information. The Ryu-Takayanagi formula, published in 2006, made this even more explicit. It showed that the entanglement entropy of a region in the boundary theory is proportional to the area of a specific surface in the bulk geometry. Geometry is entanglement. Space-time curvature, the thing Einstein said is gravity, appears to be constructed from quantum correlations between boundary degrees of freedom. If you change the entanglement structure on the boundary, the geometry of the interior changes. If you remove the entanglement, the space-time tears apart. This is not speculation. This is the most mathematically rigorous result in modern theoretical physics. And its implication is this. Gravity, the thing you feel right now pressing you into your chair, the thing that holds the solar system together, may not be a fundamental feature of reality. It may be an emergent phenomenon, a hologram, a shadow cast by quantum information processing on a surface that, from our perspective, inside the bulk, we cannot see. But here is where the discomfort deepens, beyond anything the holographic principle alone can produce. Because even if gravity is emergent, even if it is not fundamental, even if it is a thermodynamic or holographic consequence of some deeper structure, you still have to answer what the microscopic degrees of freedom are, what the boundary theory is, what generates the entanglement that gives rise to space-time. And when you ask those questions, you find yourself right back where Newton was in 1692, staring at a mechanism you cannot identify, describing effects you cannot explain. Ted Jacobson derived Einstein's equations from thermodynamics, but he did not identify the microscopic degrees of freedom. Maldacena showed gravity emerges from entanglement, but only in a spacetime with a negative cosmological constant, which is not our universe. Our universe has a positive cosmological constant. Nobody has extended AD/CFT to de Sitter space in a convincing way. Verlinde derived Newton's law from entropy, but his theory fails for large galaxies and he has gone silent. Every path to gravity is emergent, reproduces the behavior, and then hits a wall. And now consider the hierarchy problem, which sits like a splinter in the middle of all of this. Gravity is weak. Absurdly, inexplicably, outrageously weak. The electromagnetic force between two protons is roughly 1.24 times 10 to the 36th times stronger than the gravitational force between them. You can see this weakness with your own eyes every time a child sticks a refrigerator magnet to a metal surface. That tiny magnet, a few grams of material, is overcoming the gravitational pull of the entire planet Earth on the object it is holding. All 6 times 10 to the 24 kilograms of rock, magma, and iron beneath your feet, and a magnet you can hold between 2 fingers wins. Nobody knows why gravity is this weak. It is not just unexplained. It is unexplained in a way that creates a concrete mathematical problem. The Higgs boson, discovered at CERN in 2012, has a mass of about 125 giga-electron-volts. The Planck mass, the natural gravitational energy scale, is about 10 to the 19th giga-electron-volts. The gap between them is 17 orders of magnitude. Quantum corrections should push the Higgs mass up toward the Planck scale. That it remains at 125 GIH requires the various contributions to cancel each other to a precision of roughly 1 part in 10 to the 34th. That is not a small fine-tuning. That is a cancellation so exact it looks designed, and every proposed explanation for this cancellation, supersymmetry, large extra dimensions, the relaxation mechanism, has either been ruled out by experiment or remains untestable. The LHC was supposed to find evidence of one of these solutions. It found none. As of today, the hierarchy problem has no solution that has survived contact with data, and the people who work on this problem know it. The mood at major conferences has shifted from optimism to something harder to name. Not despair exactly, more like a reluctant acknowledgement that the easy answers are gone and nobody is sure what replaces them. So let us take stock of where we are. Newton described gravity as a force and confessed it was absurd. Einstein described gravity as geometry and never explained why geometry responds to mass. Quantum field theorists tried to quantize gravity and the math collapsed into uncontrollable infinities. String theorists promised a unified theory and delivered 10 to the 500th possible universes and 0 predictions. Loop quantum gravity quantized space itself but cannot recover smooth spacetime or incorporate matter. Entropic gravity derived Newton's law from thermodynamics and then failed on galaxy-sized scales. The Wheeler-DeWitt equation quantized the entire universe and eliminated time from existence. Jacobson derived Einstein's equations from heat flow. Maldacena showed gravity can emerge from a boundary theory that contains no gravity at all. Every one of these approaches taught us something real. Every one of them reproduced some or all of gravity's known behavior. And not one of them explained what gravity is. They redescribed it in progressively more sophisticated mathematical languages, in frameworks that illuminate different facets of the problem. But the core question, the one Newton refused to answer, and Einstein sidestepped, and 3.5 centuries of brilliant physics have failed to resolve, remains exactly where it started. What is gravity? Why does it exist? What is the mechanism? And the hierarchy problem just makes the whole thing worse, because it is not merely that gravity is unexplained, it is that gravity is inexplicably weak, and the weakness itself defies every theoretical framework designed to account for it. You have a force that holds together every large-scale structure in the visible universe, from planets to galaxy clusters to the cosmic web, and it is 10 to the 39th times feebler than the force that holds your atoms together. If you took every kilogram of mass on Earth and calculated the gravitational energy binding the planet together, the answer is roughly 2.24 times 10 to the 32nd joules. It sounds enormous. But the electromagnetic energy holding together the electrons and nuclei in a single gram of matter is comparable to an atomic bomb's yield. Gravity's grip on the cosmos is a trillion times weaker than electromagnetism's grip on a molecule. And nobody, in any framework, has explained why. There is a reason this particular mystery has the quiet, corrosive effect it does on the people who work on it. With the other open questions in physics, dark matter, dark energy, the matter-antimatter asymmetry, there is at least a sense of what a solution might look like. Discover the particle, measure the equation of state, find the asymmetry in the early universe. The path forward is unclear, but the shape of success is imaginable. With gravity, the shape of success is not even defined. What would it mean to explain what gravity is? What would an answer look like? Would it be a mechanism, like gears or springs? Would it be a deeper symmetry principle? Would it be a proof that no explanation exists? The field does not agree on what the question is actually asking, let alone how to answer it. But here is the thing that changed, the thing that separates the present moment from every previous decade of this story. For the first time in the history of gravity research, experiments are catching up to the questions. For most of the 20th century, gravity experiments meant one of two things. Either you were testing general relativity's predictions against observation, which everyone did and Einstein always won, or you were trying to measure the gravitational constant g with slightly better precision, which everyone did and nobody won because the measurements kept disagreeing with each other. The experimental study of gravity was, with a few exceptions, a confirmatory exercise. You already knew what the theory predicted. You just checked whether the prediction was right. It always was. And the result was a century of experimental triumph that told us absolutely nothing new about gravity's fundamental nature. The Pound-Rebka experiment in 1959 was typical of this dynamic. Robert Pound and his graduate student Glenn Rebka used the Mossbauer effect to fire 14.4 kiloelectron-volt gamma rays from Iron 57 up a 22.6-meter tower at Harvard's Jefferson Physical Laboratory. They were testing whether photons climbing out of a gravitational field lose energy, as Einstein's equivalence principle predicts. The fractional frequency shift they measured was 2.56 times 10 to the negative 15, plus or minus about 10%. Einstein was right. By 1964, Pound and Snyder improved the measurement to within 1% of the theoretical prediction. The experiment was a masterpiece of precision. A single degree Celsius temperature difference between the emitter and absorber caused a frequency shift comparable to the entire gravitational effect, meaning that temperature control had to be maintained with extraordinary care throughout the measurement. The result confirmed general relativity once again, and it told us nothing about what gravity is. This pattern, exquisite confirmation of existing theory with zero insight into fundamental mechanism, defined gravity experiments for 100 years. It is the experimental equivalent of Newton's confession. We know exactly what gravity does. We can predict its effects with extraordinary precision. We cannot explain why it does what it does, and no experiment in the 20th century even attempted to probe that deeper question, because the energy scales and mass scales where the answer might lie were utterly beyond reach. LIGO changed the landscape of gravitational observation without changing this fundamental dynamic. On September 14, 2015, at 9:50 a.m. Universal Time, signal GW150914 arrived at the two LIGO detectors in Hanford, Washington, and Livingston, Louisiana. Two black holes, roughly 36 and 29 solar masses, had spiraled into each other 1.3 billion light-years away. Their merger released energy equivalent to roughly 3 solar masses, converting it entirely into gravitational radiation in a fraction of a second. The peak luminosity of that event, the rate at which energy was being emitted as gravitational waves, was approximately 3.6 times 10 to the 49th watts. That is more than 10 times the combined luminosity of every star and galaxy in the observable universe. All the light from every source in the cosmos, and this single event outshone all of it, not in light, but in ripples of space-time curvature. And by the time those ripples reached Earth, after traveling for 1.3 billion years across the expanding universe, they changed the length of LIGO's 4-kilometer arms by approximately 4 times 10 to the negative 18 meters. 1/1000th of the diameter of a proton. To detect a signal that small, LIGO's laser interferometer had to measure the distance between mirrors with a sensitivity better than 1 part in 10 to the 21. There is no human analogy that captures what this precision means. The closest one can come is to say it is equivalent to measuring the distance from Earth to the nearest star, Alpha Centauri, 4.24 light-years away, and detecting a change of less than the width of a human hair. David Reitze, the LIGO executive director, announced the result on February 11, 2016. The 2017 Nobel Prize in Physics went to Rainer Weiss, Barry Barish, and Kip Thorne. Since then, LIGO and its partner detectors Virgo and Cagra have completed 4 observing runs. The 4th run concluded in November 2025. The combined catalogue now contains over 300 confident detections, with total candidates exceeding 400. In August 2025, the GWTC 4.0 catalogue released 128 significant events from the first half of the 4th run. Alone, the record-setting detection GW250-114 from January 14, 2025 achieved a signal-to-noise ratio of approximately 80, enabling the first confident identification of a Kerr black hole, overtone and empirical confirmation of Stephen Hawking's 1971 area theorem. On August 17, 2017, LIGO detected something even more revealing. GW170817, a binary neutron star merger roughly 140 million light-years away, a gamma-ray burst, GRB17817A, arrived just 1.74 seconds after the gravitational wave signal, after both had traveled for 140 million years. This constrained the difference between the speed of gravity and the speed of light to between -3 times 10 to the -15 and +7 times 10 to the -16 times the speed of light. Gravity and light travel at the same speed to better than 1 part in a quadrillion. That single observation, that 1.74-second gap, after a journey of 140 million years, eliminated entire classes of modified gravity theories overnight. LIGO is a monument to experimental physics. It confirmed that gravitational waves exist. It confirmed that general relativity predicts their waveforms with extraordinary accuracy. It confirmed that gravity propagates at the speed of light. It opened an entirely new window onto the universe, allowing us to observe events like black hole mergers that are invisible to telescopes. But it did not tell us what gravity is. It did not tell us whether gravity is quantum. It did not detect gravitons. It did not provide evidence for any theory of quantum gravity. It did not explain the hierarchy problem. It did not shed light on why mass curves space-time. LIGO is a listening device tuned to the symptoms of gravity, and it hears those symptoms with superhuman precision. But symptoms are not a diagnosis. LIGO confirmed everything we already knew about how gravity behaves and left the question of what gravity is exactly where it has been for 3 centuries. There is a way of thinking about this that makes the frustration more vivid. Consider what happened on June 28, 2023, when the Nanograv collaboration published 15 years of pulsar timing data. They had been monitoring 67-millisecond pulsars, dead stars spinning hundreds of times per second, with the regularity of atomic clocks, tracking the arrival times of their radio pulses with nanosecond precision. What they found was a correlated low-frequency hum in the timing residuals, a pattern that matched the Hellingsdown's angular correlation, the specific fingerprint predicted for a stochastic gravitational wave background. The Bayes factor against pure noise exceeded 10 to the 14th. The result was simultaneously confirmed by European, Chinese, and Australian pulsar timing collaborations. Physics had detected the background rumble of the gravitational universe, most likely generated by a population of supermassive black hole binaries with masses between 100 million and 10 billion solar masses, slowly spiraling together across cosmic time. This is extraordinary. This means the universe is filled with gravitational waves at every frequency. Low-frequency rumbles from supermassive black hole pairs. High-frequency chirps from stellar mass mergers. A gravitational symphony playing everywhere, at all times, that we are only now developing the instruments to hear. And in January 2024, the European Space Agency formally adopted LISA, the Laser Interferometer Space Antenna. In June 2025, ESA signed construction agreements for the 3 spacecraft that will fly in a triangular formation with arms, 2.5 million kilometers long, orbiting the Sun at Earth's distance. LISA will detect supermassive black hole mergers at millihertz frequencies, events invisible to ground-based detectors, opening yet another window onto gravitational phenomena. Its expected launch date is 2035 on an Ariane 6 rocket. We are entering an era of gravitational wave astronomy that would have been unimaginable a decade ago. Multiple detectors, multiple frequency bands, hundreds of detections per year, precision tests of general relativity in the strong field regime, and every single result, every detection, every waveform, every parameter extraction, tests how gravity behaves. Not one of them tests what gravity is. The distinction sounds philosophical until you realize that it is the distinction between a map and the territory. We are building increasingly detailed maps. The territory remains unexplored. And that is why the experiments that matter most right now are not the big ones. They are the small ones, the tabletop ones, the ones that sound almost absurdly modest next to LIGO's 4-kilometer arms and billion-dollar budgets. Because for the first time, these small experiments are probing gravity in a regime where quantum effects might actually show up. In February 2024, Tim Fuchs and colleagues at the University of Southampton and Leiden University detected a gravitational pull of approximately 30 atone-tones, that is, 30 times 10 to the negative 18 newtons. The force of gravity acting on a particle of just 0.43 milligrams, the particle was levitated in a superconducting magnetic trap, cooled to 4.48 Kel, just above absolute zero, isolated from every vibration and electromagnetic disturbance the researchers could identify. Professor Hendrik Ulbricht called the result a pivotal first step in the quest to understand quantum gravity. The measurement is a gravitational interaction at the smallest scale ever detected. It is getting close to the mass range where quantum effects on gravity, if they exist, might become observable. At MIT, Dongkel Shin and colleagues published a result in Optica in 2025 that opens a different door. They achieved the first active laser cooling of a centimeter-scale torsional oscillator to quantum-limited precision. Not a single atom, not a nanoparticle, a centimeter-scale mechanical object, cooled to the point where quantum uncertainty dominates its motion. Their next step is to place 2 such oscillators near each other and let them interact only through gravity. If gravity entangles them, if the quantum state of one oscillator becomes correlated with the quantum state of the other, purely through gravitational interaction, then gravity must have quantum properties. There is no way to produce entanglement through a purely classical channel if the interaction is local. Shin stated the stakes plainly. Theoretical physicists have proposed many possible scenarios, but the debate remains unresolved because we have never had a clear way to test gravity's quantum nature in the lab. This is the BMV experiment, named after 3 physicists, Sugato Bose, Chiara Marletto, and Vlatko Vedral. In 2017, they published 2 independent papers, both in physical review letters, proposing a specific test. Place 2 masses in quantum superposition. Let them interact only gravitationally. If the masses become entangled, and if the interaction is local, then the gravitational field must be quantum. The logic is ironclad within its assumptions. A classical field cannot generate entanglement between 2 quantum systems through local interactions. Therefore, entanglement equals quantum gravity. Nobody has performed the experiment yet, It requires placing masses of roughly 10 to the negative 14 kilograms into spatial superpositions of about 100 micrometers, maintaining quantum coherence for seconds. This is at the very edge of current technology. Multiple groups around the world are working toward it. If any of them succeed, and if entanglement is detected, it would be the first experimental evidence that gravity has quantum properties. After 80 years of purely theoretical argument, a laboratory result. But in 2025, a complication emerged that nobody expected. Nadia Aziz and Richard Howell published a paper in Nature showing that classical theories of gravity can also produce entanglement between massive particles, provided the matter itself is described using full quantum field theory rather than non-relativistic quantum mechanics. The key distinction is subtle but devastating for the BMV interpretation. The original BMV argument assumed that the matter can be treated as non-relativistic quantum particles interacting through a mediating field. In that framework, entanglement requires the mediating field to be quantum. But Aziz and Howell showed that when you treat the matter fields relativistically, the distinction between classical gravity and quantum gravity becomes murkier. The entanglement can arise from the quantum nature of the matter interacting with a classical gravitational field without the gravitational field itself being quantum. This does not mean the BMV experiment is useless. It means the interpretation of a positive result is more ambiguous than originally believed. A negative result, no entanglement, would still strongly constrain theories, and a positive result would still be extraordinary even if its implications for the quantumness of gravity are less definitive than hoped. But it does mean that the single cleanest experimental test of quantum gravity on the drawing board has become conceptually messier. The universe, as usual, is not cooperating. Then there is the graviton, the quantum of the gravitational field. Massless, spin-2, never detected, and possibly undetectable in principle. Freeman Dyson argued in his 2012 Poincaré Prize lecture that LIGO-type detectors cannot detect single gravitons. To make the quantum noise small enough to observe an individual graviton's effect on the mirror separation, you would need mirrors so massive that they would collapse into a black hole before the measurement could be completed. Rothman and Baum rigorously analyzed this in a 2006 paper and concluded that even with an ideal detector, the mass of Jupiter orbiting a neutron star, you would expect to detect roughly one graviton every 10 years. The graviton seemed permanently beyond reach. But in 2024, Igor Pikovsky at Stevens Institute of Technology and colleagues published a paper in Nature Communications arguing that graviton detection is theoretically possible using modern quantum sensing technology. Specifically, superfluid helium resonators cooled to their quantum ground state. The idea is to look for discrete energy transitions in the resonator that can only be explained by the absorption of individual gravitons from an astrophysical source. Pikovsky and Jack Harris at Yale are now building the world's first graviton detector using funding from the W.M. Keck Foundation. Harris told a reporter, "We already have the essential tools. We can detect single quanta in macroscopic quantum systems. Now it is a matter of scaling." The detector, if it works, would need to distinguish graviton absorption events from every other source of noise, thermal fluctuations, cosmic rays, seismic vibrations, at a sensitivity level that has never been achieved for any gravitational measurement. The expected rate of graviton absorption depends on the astrophysical source, but even optimistic estimates suggest waiting months or years for a statistically significant signal. And a null result would be ambiguous. It could mean gravitons do not exist, or it could mean the detector is not yet sensitive enough, or it could mean the astrophysical sources are weaker than predicted. Gravity does not make itself easy to interrogate. And at Caltech, the G-QUEST experiment, published in Physical Review X in 2025, uses tabletop Michelson interferometers with novel photon counting readout to search for space-time fluctuations predicted by quantum gravity models. The experiment was designed to test a specific proposal by Eric Verlinde and Catherine Zurich from 2021, which predicts that spacetime itself exhibits measurable geometric fluctuations at scales far larger than the Planck length. If spacetime is quantum, it should jitter, not at the Planck scale, which is permanently inaccessible, but at larger scales where the effects accumulate and become in principle detectable. The GQuest design can recover predicted signals roughly 100 times faster than traditional interferometric methods. If positive results emerge, they would provide the first empirical evidence that spacetime has a quantum structure. If negative results emerge, it would constrain the Verlinde-Zurek model and push the jitter, if it exists, below the current detection threshold. There is also a development that almost nobody outside of theoretical physics is talking about, and it concerns the nature of spacetime itself. In November 2025, Quantum magazine reported on a resurgence of interest in quadratic gravity, a quantum field theory approach to gravity that was first explored in the 1970s and then largely abandoned when string theory captured the field's attention. Quadratic gravity adds terms proportional to the square of the curvature to Einstein's equations. The resulting theory is perturbatively renormalizable, meaning it avoids the infinity problem that kills naive quantum gravity. The catch has always been that the theory contains ghost particles, excitations with negative norm that seem to violate basic physical principles, like unitarity, the requirement that probabilities add up to 1, but recent work by John Donahue, Gabriel Menezes, and others has shown that these ghosts may not be as deadly as previously thought. Under certain conditions, the ghosts can be benign, either unstable enough to decay before causing problems, or confined to energy scales where they do not affect observable physics. The theory is making a comeback precisely because the alternatives have stalled. This is telling. 50 years ago, quadratic gravity was dismissed in favor of string theory because string theory seemed to offer a more elegant, more complete solution. Now, with string theory unable to make predictions and loop quantum gravity unable to recover classical space-time, physicists are circling back to the approach they abandoned. It is as if the field has walked in a very large, very expensive circle. These experiments, the Southampton tabletop measurement, the MIT quantum oscillators, the Pekovsky graviton detector, the Guest interferometer, the global race toward the BMV test, the revival of quadratic gravity, represent something genuinely new in the history of gravity research. For the first time, the instruments are approaching a regime where they might distinguish between quantum and classical gravity. For the first time, the questions that have been purely theoretical for 8 decades are becoming empirical. This is real progress, concrete engineering-level progress. Machines being built, data being taken, results being published in top journals. And none of it will answer the question the title of this video promised you. Think carefully about what these experiments can tell us. If the Pekovsky detector finds gravitons, it tells us the gravitational field is quantized. It does not tell us why it is quantized. If the BMV experiment produces entanglement, it tells us gravity has quantum properties. It does not tell us what those properties are properties of. If GQuest detects space-time fluctuations, it tells us geometry has a quantum structure. It does not tell us why geometry exists or what it is made of, or why mass interacts with it. If the MIT oscillators demonstrate gravitational decoherence, it tells us gravity mediates quantum information. It does not tell us what gravity is. Every experiment on the drawing board, every instrument under construction, every proposal in every grant application in every quantum gravity lab on Earth is designed to tell us more about how gravity behaves, about what it does at small scales, about whether it has quantum properties, about its relationship to entanglement and information. And all of that is new. All of that extends our description into territory it has never reached. But description is what physics has been doing with gravity since 1687. The new experiments extend the frontier of description. They do not cross the border into explanation. There is a thought experiment that makes this concrete. Imagine the Pekovsky detector works. Imagine it detects individual gravitons, Headlines around the world declare that gravity has been proven quantum. The Nobel Committee makes its calls. And then someone asks the obvious question: why is the gravitational field quantized? What makes it quantum? The answer from the Graviton detection is silence. The experiment tells you that the field comes in discrete packets. It does not tell you why. It does not tell you what determines the spin of the graviton, or why it is spin 2 rather than spin 1 or spin 0. It does not tell you why the gravitational coupling is 10 to the 39th times weaker than the electromagnetic coupling. It tells you gravity is quantum the same way Cavendish told you gravity exists between lead balls. It confirms the behavior without illuminating the mechanism. Or imagine the BMV experiment succeeds. Despite the Aziz and Howell complication, two masses in superposition become entangled through gravity. This proves that gravity mediates quantum information. And then someone asks the next question: how? Through what mechanism does a classical-looking space-time geometry transmit quantum correlations? Is the entanglement a property of the gravitational field, or of the space-time itself, or of the boundary theory from which space-time emerges? The entanglement is detected, the mechanism is still missing. Or imagine GQuest detects space-time fluctuations at exactly the amplitude predicted by the Verlinde-Zurek model. Space-time is quantum. It jitters. And then someone asks the same question again. Why does it jitter in this particular way? What determines the amplitude and spectrum of the fluctuations? Why does quantized space-time produce gravity rather than something else? The fluctuations are measured. The explanation is absent. This is not a criticism of the experimenters. They are doing something extraordinary. They are building instruments sensitive enough to detect the quantum properties of the weakest force in nature at mass scales previously thought impossible, in tabletop setups that cost a fraction of LIGO's budget. This is among the most impressive experimental physics being done anywhere in the world right now. But the distinction between what these experiments can achieve and what the public has been implicitly promised is one that the physics community has not been honest about. The implicit promise, the one embedded in every popular science article about quantum gravity, every breathless press release about testing whether gravity is quantum, every documentary that frames the search as a quest for a theory of everything, is that once we figure out the right mathematical framework, gravity will be explained, that there is an answer waiting to be found, that someday a physicist will write down an equation, or build a machine, or run an experiment, and we will finally know what gravity is, that the question has an answer, and we just have not been clever enough to find it yet. And the pattern of the last 350 years suggests that promise might be empty. John Archibald Wheeler died on April 13, 2008, at the age of 96. He was the last surviving member of the generation that built both nuclear physics and the modern theory of gravity. He had worked on the Manhattan Project as a young man, then spent the rest of his career asking the deepest questions physics has to offer. What is the nature of space-time at the quantum level? What is the role of the observer in physics? What is the relationship between information and physical reality? Wheeler coined the term black hole in 1967. He coined quantum foam to describe the wild fluctuations he believed occurred at the Planck scale, where space-time itself would lose its smooth character and dissolve into a seething froth of wormholes and topological fluctuations. And in 1989, he coined the phrase that may be his most lasting contribution to the philosophy of physics: it from bit. His own relationship with gravity was marked by a personal tragedy that may have shaped his later thinking about the nature of time and reality. Wheeler's younger brother, Joe Wheeler, was killed in action in Italy in 1944 during World War II. John Wheeler, who had spent the war working on the Manhattan Project at Los Alamos, never fully recovered from the timing. He had been building a weapon of mass destruction while his brother was being killed by conventional warfare on the other side of the world. Decades later, Wheeler's work on delayed choice experiments and the nature of the past took on a different resonance when you knew this about him. His question, does the present determine the past, was not merely a physics problem. It was a question about whether the past is fixed whether the things that happened had to happen, whether different choices could have produced different histories. The physics was always rigorous, but the urgency behind it was personal. His formulation of it from bit was precise. It from bit symbolizes the idea that every item of the physical world has at bottom, at a very deep bottom, in most instances, an immaterial source and explanation. That what we call reality arises in the last analysis from the posing of yes-no questions and the registering of equipment-evoked responses. In short, that all things physical are information theoretic in origin, and this is a participatory universe. Wheeler was not a mystic. He was pointing at something specific. The deepest layer of physics, the layer beneath space-time and fields and particles, might be informational, not matter, not energy, not geometry. Information. Bits. Yes-no questions posed to nature, and gravity, in this picture, would be something that arises from the pattern of those answers. Not a force, not geometry, not entropy, a feature of the information structure of reality. It is a beautiful idea. It aligns with Jacobson's derivation of Einstein's equations from thermodynamics, because thermodynamics is about information. It aligns with the holographic principle, because holographic says the information content of a region is on its boundary, not in its volume. It aligns with Maldaceno's AD/CFT, because the boundary theory is a quantum information system and gravity emerges from its entanglement structure. It aligns with the Ryutake-Yanagi formula because that formula directly equates geometric areas with entanglement entropy. But it from bit does not explain what gravity is either. It replaces one question with another. If gravity arises from information, what is it stored? How does it give rise to the specific properties of gravity and not some other phenomenon? Why does information structured in this particular way produce a force that is 10 to the 39th times weaker than electromagnetism? Why does it produce a force at all? Wheeler spent the last decades of his life circling these questions. His students went on to revolutionize physics. Richard Feynman developed quantum electrodynamics and won the Nobel Prize. Kip Thorne co-founded LIGO and won the Nobel Prize. Hugh Everett proposed the many worlds interpretation, one of the most debated ideas in the foundations of quantum mechanics. Jacob Bekenstein showed that black holes have entropy, opening the door to the thermodynamic understanding of gravity. Every one of these lines of research traces back to Wheeler's willingness to ask questions that sounded crazy to his contemporaries. And every one of them, in the end, produced extraordinary descriptions that left the deepest question unanswered. Wheeler's most revealing habit was the question he asked at the end of nearly every physics talk he attended. He would stand up, often the most senior person in the room, and ask in his quiet voice, "How does this help us understand existence?" It was not a rhetorical flourish. He meant it. He spent his life believing that physics should not merely describe what happens, but explain why anything happens at all. And he died without getting his answer. Leonard Susskind, who would go on to become one of the architects of string theory and the holographic principle, recalled meeting Wheeler in 1961. "I was completely enthralled." John was enthusiastically describing his vision of how space and time would become a wild, jittery, foamy world of quantum fluctuations at the smallest scale. "I wanted more than anything to follow this man into battle." Susskind followed. So did an entire generation. The battle has lasted over 6 decades. The enemy has not been conquered. It has not even been clearly identified. Here is where the 350-year pattern becomes impossible to ignore. Newton described gravity as a force and could not explain the mechanism. His explanation stopped at action at a distance. Ask why masses attract across empty space, and Newton had no answer. He knew it. He said so. Einstein described gravity as geometry and could not explain why geometry responds to mass. His explanation stopped at the field equations. Ask why mass curves space-time, and Einstein had no answer. The equations described the relationship. They do not explain it. The Wheeler-DeWitt equation described the quantum state of the universe and eliminated time from the description. Ask what time is in quantum gravity, and DeWitt's framework gives you silence. A frozen, timeless wave function with no clear path back to the dynamic universe you experience. String theory described gravity as a vibration of fundamental strings and produced 10 to the 500th possible configurations with no way to choose between them. Ask why strings vibrate or why these particular vibrational modes produce gravity, and string theory points you to the landscape, which is another way of saying it has no answer. Loop quantum gravity described space as discrete and quantized, with granular structure at the Planck scale. Ask why space has this quantum structure, why it is granular rather than continuous, and the framework takes it as an axiom, an assumption, a starting point without deeper justification. Entropic gravity described gravity as a thermodynamic consequence of information and entropy. Ask where the information comes from, what the microscopic degrees of freedom are, and Verlinde's framework does not answer. It assumes a holographic boundary with information content and derives gravity from that assumption. The assumption itself is unexplained. The holographic principle and AD/CFT describe gravity as emergent from quantum entanglement on a boundary. Ask why entanglement on a boundary produces geometry in a bulk, and the duality gives you a mathematical equivalence without a physical mechanism. The equivalence is exact. The explanation of why it holds is absent. Every single one of these frameworks follows the same pattern. It reproduces gravity's behavior, often with impressive accuracy and genuine mathematical beauty. And then it hits a flaw, a place where the why questions stop being answerable, a place where the framework takes something as given, as primitive, as a brute fact that cannot be derived from anything deeper. And the flaw is always in the same place, right below whatever level of description the framework operates at. Newton's flaw was the force law. Einstein's flaw was the field equations. String theory's flaw was the landscape. Loop quantum gravity's flaw was the discrete spectrum. Entropic gravity's flaw was the holographic screen. Maldaceno's flaw was the boundary theory. The flaw moves, but it never disappears. This is the third time this pattern has appeared in this story, and by now you should feel it approaching like something you have been dreading since the opening. The first time was at the beginning, when we noted that every explanation of gravity has produced a deeper question. The second time was in the middle, when Tim Maudlin's argument raised the possibility that laws of nature are irreducible. Now, at the end, the pattern has been demonstrated across every framework, every generation, every genius. It is not a coincidence. It is not a temporary limitation. It is the shape of the problem. The philosopher Tim Maudlin at New York University has argued that this is not a contingent feature of our current ignorance. It may be a necessary feature of how explanation works. In The Metaphysics Within Physics, published in 2007, Maudlin argues that laws of nature may need to be taken as primitive, irreducible. There may be no deeper level from which they can be derived. At some point, physics reaches a place where the answer to why is simply because that is the law. Not because we lack the mathematical sophistication to go deeper, not because the experiments are too crude, but because there is no deeper. This is a profoundly uncomfortable idea for physicists. The entire enterprise of theoretical physics is built on the assumption that there is always a deeper level, that every effective theory is the low-energy limit of some more fundamental theory, that the pattern of explanation continues all the way down. Maudlin is suggesting that it does not, that somewhere the chain of explanation terminates, and the question is whether gravity is the place where it terminates. Harvey Brown at Oxford made a related argument in Physical Relativity, published in 2005. He argues that the geometry of space-time should be explained by the dynamical behavior of matter and fields, not treated as primitive. But when you push Brown's program to its conclusion, you discover that the dynamical explanation requires its own unexplained ingredients. the specific form of the matter Lagrangian, the symmetries of the fields, the existence of the fields themselves. Explanation does not terminate. It recedes, you chase it, and it moves backward at exactly the speed of your pursuit. Roger Penrose, who shared the 2020 Nobel Prize for his work showing that black hole formation is a robust prediction of general relativity, has been candid about the depth of the problem. In The Road to Reality, published in 2004, Penrose devotes hundreds of pages to the mathematical structures underlying physics and arrives at a picture he calls three worlds. The physical world, which gives rise to the mental world, which gives rise to the mathematical world, which describes the physical world. A loop with no clear foundation, no starting point, no bottom turtle. Penrose does not resolve the loop. He presents it as an open mystery, and gravity, in Penrose's picture, is the place where the loop is tightest, where the physical and the mathematical worlds press against each other most intimately, and where the gap between them is most painfully visible. Consider the evidence. 350 years of continuous effort, the most brilliant minds in the history of science, Newton, Einstein, Dirac, Feynman, Hawking, Wheeler, Penrose, Witten, Ravelli, Maldacena, Susskind, Verlinde, T. Hooft. Every one of them either worked directly on the problem or contributed tools that others used to attack it. The combined intellectual firepower directed at the question, what is gravity, over the last 3.5 centuries, is, without exaggeration, the greatest concentration of genius ever applied to a single scientific problem. And the result is a collection of descriptions, each more sophisticated than the last, none of which explains what gravity is. At some point, the failure itself becomes data. Not a single one of these frameworks was wrong in the sense that it made incorrect predictions. Newton's gravity works for everything except very strong fields and very high speeds. Einstein's works for everything except the quantum regime, string theory, loop quantum gravity, and the others make very few predictions at all. But the predictions they do make have not been falsified. The problem is not that the descriptions are incorrect. The problem is that they are only descriptions. And every attempt to push past description into explanation has produced another description sitting on top of an unexplained foundation. If this pattern were limited to gravity, you might dismiss it as a sign that the right framework has simply not been found yet. But gravity is the only force for which this pattern has persisted across every framework ever applied to it. Electromagnetism was described by Maxwell and explained by quantum electrodynamics. The strong force was described by nuclear physics and explained by quantum chromodynamics. The weak force was described by Fermi theory and explained by electro-weak unification. In each case, the deeper framework did not merely redescribe the force, it identified the mechanism. Photon exchange for electromagnetism. Gluon exchange for the strong force. W and Z boson exchange for the weak force. The pattern of description followed by explanation held for every other fundamental interaction. For gravity, the pattern has been description followed by better description, followed by even better description, and explanation has never arrived, not once, in 350 years, across dozens of frameworks. The pattern is unique to gravity, and that uniqueness is itself a clue if you are willing to follow it to its conclusion. What makes gravity different? Why is it the one force that refuses to be explained? One possible answer is the equivalence principle. Gravity is the only force that couples universally to everything. Electromagnetism acts on charges. The strong force acts on quarks. The weak force acts on left-handed fermions. Each of these forces has a domain. Gravity has no domain, it acts on all mass and energy without exception. And because of the equivalence principle, it is indistinguishable from the geometry of spacetime itself. When you try to explain gravity, you are trying to explain the stage on which all other explanations take place. You are trying to use physics to explain the arena of physics. The tool is trying to examine itself. Another possible answer comes from the Planck scale. The regime where quantum gravity effects become important is 10 to the 15th times beyond our experimental reach. For electromagnetism, we could build accelerators that probed the relevant energy scale. For the weak force, the W and Z bosons appeared at energies the LHC could reach. For the strong force, asymptotic freedom was confirmed at energies available to existing colliders. For gravity, the relevant energy scale is the Planck energy, 10 to the 19th gigaelectron volts, and no conceivable technology can reach it. We are trying to explain a phenomenon whose fundamental behavior occurs at a scale we cannot probe, in a regime we cannot access, at energies we cannot produce. We are trying to explain the workings of a lock without being able to see the key. But there is a third possible answer, and it is the one that fits the 350-year pattern most tightly. Maybe the reason gravity cannot be explained is not that we lack the tools, or the energy, or the mathematics. Maybe it is that gravity is the place where the chain of physical explanation terminates. Not because gravity is complicated, but because it is fundamental in a way that other forces are not. Electromagnetism, the strong force, and the weak force can all be explained in terms of quantum field theory, gauge symmetries, and the exchange of mediating particles. These explanations work because the forces are properties of fields on a background spacetime. The background exists independently of the forces. You can explain the forces in terms of the background. Gravity is the background. It is not a force acting on spacetime. It is spacetime, or a property of it, or equivalent to it. And you cannot explain the background in terms of itself. There is nothing behind the curtain. The curtain is what there is. And this may be the deepest reason that every attempt to explain gravity produces another description rather than an explanation. Every framework that tries to explain gravity must assume something, some starting point, some foundation, some primitive ingredient that is itself unexplained. And that unexplained ingredient always turns out to be another way of saying gravity, strings that vibrate, spin networks that quantize area, holographic boundaries that encode information, entropic forces that emerge from statistics. Each of these is a description of the foundation. The foundation itself remains beyond the reach of explanation. There is one more piece to this that makes the picture complete, and it comes from an experiment so precise, so exquisitely sensitive, that it almost makes the problem worse. In 2015, LIGO detected gravitational waves for the first time. Two black holes, each roughly 30 times the mass of the Sun, spiraling into each other and merging. The event radiated energy equivalent to 3 solar masses as gravitational waves. At peak luminosity, the power output exceeded 10 times the combined light of every star in every galaxy in the observable universe. And by the time this staggering output crossed 1.3 billion light-years of space, it moved LIGO's mirrors by 4 times 10 to the negative 18 meters, 1,000th of a proton's width. Now consider what this means. The strongest gravitational wave event observed in human history, an event that briefly outshone the entire universe in gravitational radiation, produced a physical effect on LIGO's mirrors equivalent to moving them by a distance thousands of times smaller than an atomic nucleus. That is how weak gravity is. Even its most violent, most energetic, most cataclysmic expressions produce effects so small that detecting them required building the most sensitive instrument in human history. And the gravitational constant g, the number that tells you the overall strength of gravity, is still the least precisely known fundamental constant. After Cavendish's first measurement in 1798, over 300 experiments have tried to improve it. The current best value has a relative uncertainty of about 47 parts per million. That is roughly 10,000 times less precise than the fine structure constant. And recent measurements do not converge. They scatter. 2 measurements made in the same laboratory using different methods often disagree by more than their stated uncertainties. A 2018 review noted that the spread in recent high-precision G measurements cannot be explained by known systematic errors. Something about gravity resists even being measured accurately, let alone explained. Think about what it means for a constant to resist measurement. We are not talking about a quantity that is hard to access, like the temperature at the center of a neutron star. G acts between objects on your desk. Cavendish measured it with lead balls in a shed. And yet, 227 years later, we cannot agree on its value to better than 5 significant digits. Every other fundamental constant has yielded to precision measurement. Gravity's constant has not. It is as if the number itself is slightly fuzzy, as if the thing it describes does not hold still long enough to be pinned down. That may sound like mysticism. It is not. It is a description of the experimental data. The scatter in G measurements is real, documented, and unexplained, and it sits alongside every other feature of gravity that resists being nailed down. The mechanism Newton could not identify, the geometry Einstein could not explain, the quantization that produces infinities, the unification that produces landscapes, the weakness that requires fine-tuning, the constant that will not converge. Gravity is the thing that does not cooperate. And the irony is suffocating. We live in gravity. We evolved in gravity. Every structure in the visible universe exists because of gravity. The galaxies formed because gravity pulled matter together. Stars ignite because gravity compresses hydrogen. Planets form because gravity accretes dust. Life exists because gravity held an atmosphere to a rock at the right distance from a star. You are the product of gravity. You were assembled by it atom by atom over 4.5 billion years. It is the most intimate force in your existence. And it is the one thing in physics that we cannot explain. Not, will not. Cannot. The most personal force in nature is the most fundamentally mysterious. There is a particular cruelty in this. The 3 other fundamental forces, the ones we can explain, are in some sense alien to everyday experience. You do not feel the strong force. You have never directly experienced a W boson exchange. Even electromagnetism, which governs light and chemistry and nerve impulses, is felt indirectly through its effects on matter. But gravity you feel directly, constantly, from the moment you are born. It is the weight of your body in a chair, the arc of a thrown ball, the tide pulling at the ocean, the feeling of falling. Gravity is the force you know in your bones, literally, because it is the force your bones evolved to resist. And it is the one you understand least. The other forces were explained within decades of being properly described. Maxwell described electromagnetism in the 1860s. Quantum electrodynamics explained it in the 1940s and 50s, roughly 90 years from description to explanation. The weak force was described by Fermi in 1933. It was explained by the electroweak theory in the 1960s and 70s, roughly 40 years. The strong force was described through nuclear physics in the 1930s and 40s. Quantum chromodynamics explained it in the 1970s. Roughly 30 to 40 years, gravity was described by Newton in 1687. It has been 338 years. The explanation has not arrived, and the gap between gravity and the other forces, measured in years of unresolved mystery, is not closing. It is widening, because the other forces are done. They have been explained. Their books are closed. Gravity's book is still open to the first page. And so here we are, at the bottom of a descent that began with a falling apple in 1665 and passed through curved spacetime, frozen wave functions, vibrating strings, holographic boundaries, and tabletop interferometers. The instruments are more sophisticated than anything Newton or Einstein could have imagined. The mathematics is more advanced than anything Wheeler or DeWitt had access to. The experiments are probing regimes that were considered permanently inaccessible a decade ago. And the question is the same. What is gravity? What is it made of? Why does it exist? Why is it so weak? Why does mass curve spacetime? Why does spacetime have quantum fluctuations, if it does? Why does entanglement produce geometry? Why does thermodynamics give you Einstein's equations? What is the mechanism? What is the thing beneath the description? The pattern of the last 350 years offers an answer, but it is not the kind of answer that satisfies. It is not a mechanism. It is not an equation. It is not a particle, or a field, or a symmetry principle. The answer the pattern offers is this. There may not be a mechanism, there may not be a thing beneath the description. Physics may be structurally incapable of explaining what gravity is, not because physicists are not smart enough or the experiments are not sensitive enough, but because explanation itself has a limit, and gravity sits on the other side of it. Every other force in nature has yielded to the pattern of description followed by explanation. You describe the behavior, then you discover the mechanism, then you understand why. Electromagnetism. The strong force. The weak force. Description, then mechanism, then understanding. Gravity has been described more precisely and more beautifully than any other phenomenon in physics. The descriptions are confirmed to extraordinary accuracy. The mechanism has never been found. In 3.5 centuries, across every framework, by every genius who ever turned their attention to the problem. If you had a disease, and every treatment ever tried over 350 years had reduced the symptoms without curing the underlying condition, and if the list of physicians who had tried included every great doctor in history, you would at some point have to consider the possibility that the disease is not curable. Not because of a limitation in medicine, but because of the nature of the disease itself. The physicists who have spent their lives on this problem are beginning to consider this possibility, even if most of them will not say it directly. You can hear it in the silences, in Verlinde's decade of no publications, in the failure to organize String's 22.6, in Hossenfelder's exit from academia, in Ottenheim's 5,000 to 1 bet against the consensus of his own field, in the Wheeler-DeWitt equation sitting unsolved for nearly 60 years, in the quiet, gradual acceptance that the next generation of experiments will tell us more about how gravity behaves, not what it is. Newton knew. He felt it in 1692 when he wrote to Bentley that action at a distance was an absurdity. He felt the flaw beneath his theory, the place where explanation stopped and description was all that remained. He responded with, "Hypotheses non fingo. I will not pretend to explain what I cannot explain." It was the most honest thing he ever wrote, and every physicist who has worked on gravity since has, sooner or later, arrived at their own version of the same confession. Einstein's version was the field equations beautiful and unexplained. DeWitt's version was the frozen wave function, correct and incomprehensible. Verlinde's version was the entropic derivation, elegant and incomplete. Maldasena's version was the duality, exact and mysterious. Each of them gave us a new floor to stand on, a new place from which to see further, a new description that was more precise, more powerful, more illuminating than the one before it. And each of them left the same hole in the same place, the place where the why should be. Consider the arc of this story as a whole. In 1665, a young man watched an apple fall and asked why. In 1713, after building the most successful theory of nature the world had ever seen, he admitted he could not answer his own question. In 1915, after an 8-year struggle that nearly broke him, Einstein replaced Newton's theory with one that was more accurate, more complete, more beautiful, and equally silent on the fundamental question. In 1967, DeWitt wrote down the quantum equation for the entire universe and found that it contained no time. In 2006, after half a century of work, the two largest research programs in quantum gravity were publicly criticized by respected scientists for producing no testable results. In 2010, the most radical reimagining of gravity in a century was proposed, celebrated, and then quietly abandoned when the data did not cooperate. In 2023, a physicist placed a 5,000 to 1 bet against the foundational assumption of his entire field. In 2024, the most prominent public critic of theoretical physics left academia to become a content creator. That is not the trajectory of a problem being solved. That is the trajectory of a problem revealing its nature. You have been sitting with this question now for nearly 2 hours. You have followed it from a falling apple in Plague-era England through the most sophisticated mathematics and the most sensitive experiments ever devised. You have watched the greatest minds in the history of science throw everything they had at this question and come away each time with a better description and no explanation. You have seen the pattern repeat across 3 centuries, 4 frameworks, 5 continents, and countless careers. And you are in exactly the same position Newton was in 359 years ago. You know what gravity does. You know how it behaves. You know its equations, its predictions, its effects. You can calculate orbits. You can predict eclipses. You can detect waves in space-time from 1 billion light-years away with instruments that measure changes smaller than a proton. And you do not know what it is. Neither does anyone else. Not the people at CERN, not the people at the Perimeter Institute, not the people building Graviton detectors at Yale, or quantum oscillators at MIT, or interferometers at Caltech. They will learn more about how gravity behaves. They may discover whether it is quantum, they may detect gravitons, they may observe space-time fluctuations. Each of these results would be historic. Each would extend the frontier of description into territory it has never reached. But the question that Newton could not answer, the question that Einstein sidestepped, the question that has broken the careers and the spirits and the reputations of some of the most brilliant people who have ever lived, that question will remain. Gravity holds you to the Earth right now. It holds the Earth to the Sun. It holds the galaxy together. It shaped the large-scale structure of the entire universe. It is the first force you experienced as an infant, and the last force that will act on your body when you die. It is the most universal, most inescapable, most intimate phenomenon in the physical world. And after 350 years of trying, with the combined intellectual effort of every great physicist since the invention of physics, nobody can tell you what it is. The equations are flawless. The predictions are confirmed. The descriptions are beautiful. The explanation is missing. And the people who have spent their lives searching for it are not getting closer. They are getting quieter. That silence is the most honest answer gravity has ever given us.